Alcohols, because they have an OH group on them, and haloalkanes are much like this too, with their chlorine or their bromine or their iodine group or their fluorine group. They can exhibit two different types of isomerism. Unless they're cyclic, they can't exhibit cis-trans, so geometric isomerism. Okay? So we're not talking about cyclics. They can't do that because they don't have a double bond necessarily. If they have a double bond, they're an alkene as well, instead of alkene. We're talking about things that are saturated, so carbon-carbon single bonds, and we're talking about them having an alcohol group, or, as we get on to next, a chlorine or a bromine or something like that, halogen. The first type of isomerism is one that we've met heaps, and we should be getting pretty good with, particularly with these molecular models we're using, and that's structural isomerism. We basically move the OH group around and maybe try to put a methyl group side chain on it, that sort of thing. And whenever we play with these, we can see there's a few possibilities. We can then classify them as primary, secondary, or tertiary, depending how many carbons the COH is bound to. So, quite clearly, we could have CH3, CH2, CH2, CH2OH. I'm putting the bond there on purpose to show that single bond primary. Okay? So we've got 1-butanol or butan-1-ol. Both are correct names. There is actually another primary one that we could have here. We could move the CH3 and put it on that carbon, and it will make a new molecule. So I can have CH3, CH, CH2OH, and this is still got 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens and an OH group. Okay, so this is the carbon number 1 because it has the functional group on it. So you don't need the 2 to be honest, but 2-methyl propan-1-ol or 1-propanol. 1, 2, 3 carbons in the main chain. These are both primaries because the COH is only bound to one more carbon directly. Okay, so these are structural isomers because I've changed the bonding of it, changed how things are bound, the order that things are in. These will have slightly different physical properties. Maybe not chemical properties, but definitely physical, slight differences due to the shape of their electron cloud. We could have also moved the OH group. And if we move the OH group from here to here, we create a secondary alcohol, as we saw yesterday. And this is one we're going to look at a bit in a moment, 2-butanol, because you are asked to make 2 molecules with this structural formula, but that looked different when we made them with models. I'll show those from one of the students in a moment. And then we could also move this up to here, to CH3. Well, that would give this carbon 3 carbon-carbon bonds to make it tertiary. So 2-methyl propan-2-ol. Alright, so these are all structural isomers of C4H9OH. However, as I've just alluded to, there is another type of isomerism. And here, hopefully I get this on the screen nicely, that you can see it, I've got 2 versions of the same molecule. But if I look at them in any detail, I can see that even though the order of the bonding is the same, CH3, CH2, CHOH, CH3 is the same in both of these, they actually are not superimposable. I can't put one on top of the other and have all the atoms line up the same. I end up with one hydrogen sticking out that way, for this one, and one with a hydrogen sticking out that way. So, in everyday language, what would we call those? What sort of images would we call those? Where they look the same but back to front. Mirror. They're called mirror images. Non-superimposable mirror images. In chemistry, we call these enantiomers or optical isomers. Enantiomers is the other name you will see used, so you have to know these are interchangeable. What we look for is a carbon that has got 4 different groups or 4 different atoms bound to it. And here we can find one. this one's got 3 hydrogens, so it doesn't count. That one's got 2, so it can't be that, and it can't be that one. So it must be the middle one. It's got a CH3CH2, which is different to a CH3. I know they're carbon-carbon bonds, but it's the whole group you look at. So these are different. H is different to those again, and OH is different to those again. So it has 4 different atoms or groups of atoms. That's the way we phrase it. 4 different atoms or groups of atoms. We call this carbon a chiral or asymmetric carbon. Okay, it's a chiral or asymmetric carbon. Both of those words you're allowed to use in assessment answers. So what we do is we draw a 3-dimensional diagram around that carbon to show that these are optical isomers. So I draw that carbon number 2 is my middle one, and then I try to see how it looks. Now you won't have the models in exams, so this is a good opportunity for you to see what I mean. I'd like you to have it so that the CH3CH2 is sticking straight up, please. I would like you to have it so that the, what will I choose? Let's say the CH3 is pointing down but away from you. Okay, so we're going to have the CH2, CH3 sticking straight up. You're going to have the CH3 group sticking down but away from you, please. And hopefully that will make the other 2, the H and the OH, stick out towards you. Okay, see if you can arrange them that way. Alright, so they become the feet, as it were. CH3 sort of is going to help hold up the H and the OH. So the CH3 coming away. That looks brilliant. Well done. Now it will depend which isomer you've grabbed as to whether the hydrogen is on your left or your right. But this dashed line means that it's going away from you. This triangle, or my poor attempt at a triangle, means that it's coming towards you. But we can't show 3 dimensions on a 2-dimensional piece of paper. So this is how we show it. So if, for example, the one you're holding has hydrogen coming out towards you on the left and OH on the right, you draw it that way there. Then if you do the same arrangement with your other enantiomer that you made, you'll notice that it does the opposite to it. You'll have OH coming out on the left, bless you, and H on the right. And as we looked at before with those 2 models that I borrowed, they are mirror images of each other. Well, so what, to be honest, because they have exactly the same chemical properties, by the way. Same density, same boiling point, same melting point, same chemical reactions. So what? Well, the so what is about 2 things. One is you can actually tell them apart if you have pure solutions of both of them. When we pass plain polarised light, that's the light that goes through your sunglasses, if we pass that light, a beam of that light, or a line of that light through a solution of one of these, one of them will actually rotate it, not refract, rotate it anti-clockwise, while the other one will rotate it the other way, rotate it clockwise. They rotate plain polarised light in opposite directions. So the key word for this now is, where can I put it? Okay, so they rotate plain polarised light in different directions. Okay? That's how we detect their existence. That's how we found out they exist, basically. They had this one different property. But again, I sort of come back to, so what? Who cares? They've got the same chemical reactions. As a chemist, who cares? But as a biochemist, this becomes a little bit more relevant. Nature makes enzymes called proteins, with proteins, okay? So they're made of proteins. These enzymes have a particular shape. This shape is determined by the interaction between the amino acids in that polypeptide chain that makes the protein. Some of the functional groups can interact with each other. Amino acids, all except for one of them, exist as optical isomers. All of them exist, apart from one, as optical isomers. Nature selects for only one of the optical isomers of amino acids. If it didn't, then it would have no control, as it were, over the shape, the three-dimensional shape of a protein. So these are important for biochemistry, not necessarily so much for alcohols, but when we get to amino acids, because amino acids are always one optical isomer, and because of this, when they form polypeptide chains and they fold in 3 dimensions, they always are the same shape. And it is because of that shape that, for example, alcohol dehydrogenase will successfully break down ethanol into something you can use as an energy source. Why certain enzymes will break down sugars. It's their shape of their active site. Why hemoglobin, once you put the 4 proteins together with the heme group in the middle, why that can carry oxygen and carbon dioxide successfully, but not other waste products or useful chemicals. It is that 3-dimensional shape, and it is determined by enantiomers, the fact that nature only chooses one. So therefore, when the protein breaks down things or makes things, it only makes one of those enantiomers as well, because that's the right shape for it. Okay, so that's the relevance of that. As far as it comes to alcohols, they're a really good, simple example to show that you understand how to identify enantiomers and draw 3-dimensional diagrams of each. You will have seen I put a line down the middle. That's my mirror line for my own brain to work out what to do. I draw the same shape around the same carbon on each side, and then I just mirror image the 2 on the sides. Okay, stays the same down the centre, because in a mirror line, the centre line stays the same. Okay, any questions before I turn that off?